Hi class, this is your instructor, Skylar Huff, and we're back with yet another lecture. We're now here in Chapter 2. So Chapter 2, as titled, is the chemical basis of life. Let us begin. So if anyone wants to know why chemistry is studied in the Human Anatomy and Physiology course, the reason being is chemistry underlies everything going on in the body, meaning that with what's going on, it's the chemistry that's behind the composition of substances such as hydrogen ions or hydroxide ions. It's what we eat that has that chemical basis, meaning not just what we eat, being what's in the food, but also what makes up us, what makes up you and I. I was speaking today thinking about what makes up bone. Well, those calcium phosphates are there that make bone quite strong. And not just that, but also the medications that will be administered in your not so distant future. So everything we do here is based in chemistry. So let us get down into that chemical basis of life so that by having this chemical basis of life, it'll better undergird what we do with those physiological processes that are to come. First things first, with chemistry, is just considering that composition of those substances and how they change. So there's no way this class could be taught without it. And the very same way we would also add to this biochemistry, which I didn't mention. But with that, biochemistry just brings in the biological chemistry portion of it. So of course, how these living organisms and chemistry work together. So now I'll get to matter. Matter class, and this isn't a chemistry course, but matter class is of course anything that has mass and of course takes up space. So this includes those solids, liquids, and gases. Up next, we have those things known as elements. So when I think of elements, I think of that periodic table that I've seen in many, many days back, I guess we'll say, dating back to high school and college as an undergraduate. So an element is that simplest example of matter with the specified chemical properties. So you could look at elements such as carbon, hydrogen, nitrogen, oxygen, sulfur, phosphorus, calcium, potassium. I'll stop. But I could also mention, of course, sodium and even iodine and iron. So next up, having done atoms in the structure of matter, there are elements within the body that are in, I guess I'll say, a bulk form, meaning we have to have a large amount of this, such as C, H, N, O, P, and S. I gave you those, of course, by way of their chemical symbol. So next up are the traced elements, and these are, of course, needed in a very, very small amount, such as iron and iodine. It also includes manganese, zinc, and fluorine. So having done such things, it lists some of those right here before you all. I'll continue for the essence, or at least for time's sake. So now we get on down to the atom. So as mentioned in our prior lecture, it's that smallest unit of an element that retains the chemical properties of that element. So now that we've done that, just keep in mind that the atom is made up of those subatomic particles known as the proton, the neutron, and electron. So protons carry that positive charge, neutrons carry that no charge or being neutral, and then the electrons carry that is called the negative charge. So when I get to this, just keep in mind that the nucleus is composed of both protons and neutrons, and those electrons will, of course, orbit around the nucleus. So with this, some atoms do combine with atoms that are, of course, like, or even other atoms by way of chemical bonds, and we'll get to chemical bonds here shortly. But do keep in mind, since I mentioned atoms and the periodic table of elements, just keep in mind that for a given element that the number of protons, of course them carrying that positive charge, is equal to the atomic number. So with that being stated, neutrons, which are neutral, they have, of course, can be determined by taking that atomic mass and then subtract the atomic number from that. And thirdly, electrons. Electrons are equal to the atomic number. So given a problem, hopefully you all can determine all three of those, given, of course, appropriate information. For instance, given that is called krypton, symbol Kr, with an atomic number of 36 and an atomic mass unit being 83.8, can you all now calculate the number of protons, neutrons, and electrons? Given the time, there are 36 protons, 48 neutrons, and 36 electrons. Let us continue. So from here, we get down to the, excuse me, this is what we just did, so I'll skip through this. We'll get now, class, to isotopes. So isotopes, what they have, of course, they have atoms that have the same atomic number, but of course what's different is the atomic weight. And along with this, they also differ in the number of neutrons. So of course, many times isotopes are referred to as being radioactive. So isotopes are used many times in the clinic. So you could use radioactive iodine to destroy those cancerous thyroid tissues. And the very same way, isotopes can also be used to detect coronary blood vessel disorders. Those radioactive isotopes can be also used to evaluate kidney function and even to assess changes in bone density. And even back before now, you also likely learned in your first biology course how radioactive isotopes were used to, of course, trace in an experiment. And I'm referring to, of course, Hershey and Chase's seminal experience with the experiment with the DNA. So on to a couple of more terms and then we'll get to where we're going. So molecules versus compounds. So I'll just bluntly define a molecule as being formed when you have two or more atoms chemically bonded together. So when they chemically combine, are referred to a molecule sometimes as being, of course, two hydrogens bonded together. So you have hydrogen gas, H2. The very same could be stated about, of course, O2 being oxygen gas. Whereas opposed to the compound, a compound, of course, is formed when you have two or more atoms of different elements that are combined there chemically. So I think of the compound as being, of course, such as H2O, as you see on your screen, being a molecule of water. The same can be stated about C6H12O6. That, of course, will come up many, many times, and that, of course, is a molecule of glucose. Having done those, it just now, class, shows the difference between. Here on the left, we're showing you, of course, H2, so those two hydrogens are there, and of course O2, those two oxygens there that are double bonded together. On the right hand side, we show you now the compound of water being H2O. So from here, to get to chemical bonding, we must of course go through electron shells and of course the octet rule. To make this simple, class, I'll just say that that first energy shell only holds 2 electrons, the second energy shell holds 8 electrons, and the third shell holds 8 electrons. For chemical bonding, it's the case that these atoms strive to fill their outermost shell, or their valence shell. So by way of the octet rule, you've now been given it by way of these electron shells. So let us begin with the bonding of atoms. So ion versus cation versus anion. So the positively charged ion is called the cation, and that is called a negative charge ion. The negatively charged ion is the anion. So when I refer to the term ion, I'm just referring to, of course, an atom that has gained or lost an electron, hence it carries a charge. That is nothing more, class, and that was what an ion is. So let's begin with that first of 3 bonds, I guess I'll say important biologically. And yes, that's my daughter. Yes, you're okay, buddy bud. That is you making a video. So the first bond is that ionic bond. I'll make it blunt. The ionic bond, it is formed when, of course, electron is transferred. So if you look closely here at this figure, I'll call this figure 2.4, 2.4a. This shows the sodium atom, and it also shows a chlorine atom. The sodium atom has but only 1 valence shell electron. So I would hope you know that it's easier, of course, to donate 1 electron than to gain 7 electrons. So what then happens is that one electron in the valence shell of sodium is transferred over to the chlorine atom, which I'll help you out. It has 1, 2, 3, 4, 5, 6, 7 valence shell electrons. And by the transfer of that electron class from the sodium to the chlorine, we now get what is called sodium chloride, and the sodium becomes positively charged, and the chloride is now negatively charged, and we now have sodium chloride. We call this salt. So it's typical, of course, for these ionic bonds to form what are called salts. Up next is the covalent bond. To help you out, class, I call the covalent bond that strongest bond, as opposed to what we saw with the ionic bond. To help you with it, the ionic bond is quite strong too, but I say it's strong when it's dry, and they are weak when they're wet. So in covalent bonding class, it is the sharing of electrons that occurs. So as the electrons are shared, well, that's all that is to it. So to help you out here, we have here in figure 2.5a, a hydrogen atom here on the left, and a hydrogen atom there on the right, divided by that plus sign, or at least subdivided or divided by the plus sign. So each of those hydrogen atoms have but only one electron in their valence shell. Knowing what we now know about the octet rule and valence electrons and electron shells, neither of those have a full valence electron shell, each of which needs just one more electron. So of course, from left to right as we proceed, we now get this covalently bonded class hydrogen molecule, where each of those hydrogens now are sharing that electron, and we now have H2, a molecule of hydrogen. There you have it. So it shows you in this example, in figure 2.5b, the way in which water is known as that polar covalent. So as you see, without that covalent bond, there are not full electron shells for what we call water. However, as the electrons are shared from those two hydrogens with what we have with oxygen already, looking closely you all, knowing that hydrogen has one valence electron, that means oxygen has 6 valence electrons aside from that. So by sharing one electron from each of those hydrogens, we now get H2O. And each of those, meaning the hydrogen, the second hydrogen, as well as the oxygen, all three of those have full valence shells. Hence, water is referred to as being a polar covalent. I'll get to that polar portion in just a moment. So this shows structural formulas, and I use structural formulas many times as I do teach this, but right now I'm just using the presentation being depicted. So I go back to being polar covalent. So it's polar because it's from that unequal sharing of electrons. So in this case, the oxygen class is that slightly negative portion, and what you see now here is going to be those hydrogens, which are that slightly positive charge. So the third and final bond that we'll do here in biology, or human anatomy and physiology rather, is going to be the hydrogen bond. So that hydrogen bond is that weak attraction between a slightly positive, meaning that slightly positive hydrogen, and that slightly more negative oxygen in. So this is formed between two different or separate water molecules. So to help you with it, just keep in mind it's between two water molecules. So you must have the oxygen of this water molecule bonded to the hydrogen of that water molecule. So that is the essence of the hydrogen bond. So the hydrogen bond is, I say, what makes water be what it is. So yes, it requires a lot of energy to break those bonds, hence that polar covalent it is, but it also is what's responsible for many of those properties of water. And you say many properties? Yes, indeed. I mean, such as keeping our body temperature where it is. And not just that, but also its adhesive properties, and of course, its cohesive properties. So up next are chemical reactions. So a chemical reaction, as it occurs, it always will proceed, beginning with reactants and of course yielding products. So as we've stated in such a way, I typically write this from left to right. I said typically. So being shown here in our example is sodium chloride, and as it's broken down of course into sodium and chlorine. So as this is occurring, it's just giving you that dissociation of sodium chloride in water into the sodium and chloride ions. So from here, just keep in mind that the ion is an electrically charged particle. And we'll get to that more so in just a moment. So let's get to reactions. I'll deal with at the very least the first two. The synthesis reaction. So a synthesis reaction is a reaction that makes a more complex chemical structure. So we have A plus B, which yields AB. Are you all right, buddy bud? Yes, Daddy's making a video. So keeping in mind, we took what was separately A and what was separately B, and we made what is more complex called AB. That is that synthesis reaction. So the very same way, we could go to that decomposition reaction. So in the decomposition reaction, these bonds here are broken to take what was more complex into its component parts, simpler parts. So, of course, you can just look at it right here, such as being molecules of water can decompose to, of course, the products hydrogen and oxygen. So what was once H2O is now those two hydrogens and the oxygen, of course, separately. So I won't deal so much with the reversible or exchange reaction here at the moment. But do keep in mind that catalysts, they do indeed influence the rate of reactions. But of course, they do not have anything to do with the direction of the reaction. And just keep in mind that those catalysts, known as enzymes, you all, are not consumed by those reactions. So now on to electrolytes. So with electrolytes, just keep in mind that as a result, having those charged particles from what is salt, as it dissociates into water, you get sodium ion and chloride ion. Well, it makes those what are called electrolytes, and it's simply because they are an electrically charged particle, which what an ion is. So, keeping in mind here, getting into what is called acids and bases. So, with acids and bases here, what I'll do with those is just break it down to what it is, I guess, simpler and simply. So electrolytes that dissociate to release hydrogen ions in water are called acids. Simple, class, please write that down. I'll say again, electrolytes that dissociate to release hydrogen ions in water, such as you see in this hydrochloride, giving off hydrogen atom and chlorine, or this chloride, hydrogen ion, and the chloride ion, that makes it, of course, the acid, as opposed to the converse being that known as a base. So bases are substances that release ions that combine with hydrogen ions. I repeat, they combine with hydrogen ions. So what happens here is we have this called sodium hydroxide. So what sodium hydroxide does is it releases hydroxide ions, and of course they combine with those hydrogen ions to form water. So you of course have H2O. And then finally, class, salts. So bases can react with acids to neutralize them, forming water and electrolytes known as salts. So in the example you all are seeing here, we have what is called hydrochloric acid and sodium hydroxide, and they react to form water and sodium chloride. There you have it, class. So what we'll get to here is I've already gotten to the electrolyte, so I'll move on from this. What I'll get to now is acids and base concentrations. So what I'm getting to here is that if it's an acid class, it has a higher hydrogen ion concentration because pH class is nothing more than that measure of hydrogen ion concentration. So having done it this way, just keep in mind that the pH scale, as it is simply there, I say again, to give you the power of hydrogen ions. So with this, the pH scale runs from 0 to 14. And to help you out, class, if a solution has a pH that is less than 7, the solution class is acidic. And if that solution has a pH that is greater than 7 class, that solution is basic or alkaline. The pH of 7 class is neutral, as are most bodily fluids. So having done that, I guess one last thing to say about that is just keep in mind how this hydrogen ion concentration and pH works. If you look closely, class, if I were to ask you in your test, how does the hydrogen ion concentration compare between a solution at pH 6.4 and a solution at pH 8.4? How do they compare? So I said a solution that is 6.4 compared to a solution that is 8.4. The way in which they compare, class, is that the pH of 6.4 has 100 times the hydrogen ion concentration of that solution at pH 8.4. So the reason for that is because the power of 10, class. Meaning it's 2 powers of 10 that make that difference. So please keep that in mind if, in fact, class, on the test, I ask you a question dealing with how 2 solutions compare based on the hydrogen ion concentrations. So to continue where I left off, the pH scale is there, class. I went over being basic or alkaline, and of course being neutral. So to help you out with that, I say again, acids have a greater hydrogen ion concentration, bases have a greater hydroxide ion concentration, and of course, if in fact that solution class is neutral, the concentration class of hydrogen ions as well as hydroxide ions is equal. To help you with this, class, if you look closely, right now I'm looking at what is called figure 2.10, and in figure 2. I hear you, girl. In figure 2.10, it just gives you some common household solutions and their approximate pH. So I didn't have coffee today, but if I did have coffee, it would be right there, class, being acidic. And the very same could be said, class, about the orange juice I didn't have this morning. And then on the other side of things, egg whites, class, are basic. And even more basic than such, class, is milk and magnesia. And even, class, household bleach. Please watch out for those things. So now, class, I'll get to what's important, class, in the body. This is on page 69 of your textbook, class. I say this is important to know and learn. Let us begin. Yes, I know. Daddy's talking to you. Okay, I'll get you out. Yes, Daddy will get you out. We'll get you out. Yeah. All right. So here, class, I'm getting to those negative feedback mechanisms. So this goes right back to where we were in chapter 1. So what I'm getting to here is the importance, class, of the underlying chemistry in the body and what occurs when there is some change. Let us begin. So the first condition given to you, class, is called, I guess I'll begin with acidosis. And let's go backwards just a bit. Here is a set point for you all, and if I were you all, I'll be writing these set points down. That way you don't just have them said or given in the text, but these are things that you know and have learned. So the pH of blood, class, is between 7.35 and 7.45. Please write that down and know that. So having done that, what happens, class, is because the pH of blood is normally slightly alkaline, notice 7.35 to 7.45, it needs to be a term that can be used other than being acidic and alkaline to, of course, refer to abnormal blood pH. So what I'm getting to is if a person, class, has a pH in their body that is an approximate, I guess I'll say, between 7.0 and 7.3, that person is referred to as having acidemia. I repeat, they're referred to as having acidemia. So let's get to this condition known as acidosis, based on acidemia. So if in fact, class, someone has acidosis, they may very well feel disoriented and fatigued, and likely, class, has a difficulty breathing, and even has what is called a bit of, I guess I'll say, hypoventilation. And I did say hypoventilation, having trouble breathing, meaning hypoventilation, class, would be, of course, too few breaths. So what happens as a result of this, class, is because of the diarrhea, or even, class, the severe vomiting, meaning avoiding, class, those alkaline contents of the small intestine. Notice I said the small intestine is a bit alkaline because of course it's nothing class like the stomach, which of course is acidic. So with this, diabetes mellitus, impaired breathing, lung disease, and kidney disease are all known to a cause class, acidosis. So now that we've learned about acidemia, of course with that associated condition class known as acidosis, let's now move on class to the converse. So if the blood pH class is at 7.5 or to 7.8, meaning in that range, 7.5 to 7.8, the person is referred to as having class alkalemia. So the condition that, of course, goes along with the class is known as alkalosis. So with that class, this may make someone class feel what is known as being agitated or dizzy. So the condition could be caused class by breathing rapidly at high altitudes, known as hyperventilation. So please keep these prefixes class with you. I said hyperventilation, taking those very fast breaths. Or you could be taking class too many antacids, having high fever, or just by anxiety, or just mild to moderate class vomiting. So by doing that, you're ridding class the body of the stomach contents, the stomach acid that should be there. Please learn both of these class and look for them in your test. So next subclass is what is known as the buffer. So a buffer is here class, and what that buffer does is nothing more than resist change in pH. Please class, write that down and learn it. The question class asks, what is a buffer? A buffer class functions to resist change in pH. So what happens class with buffers is they bind and release hydrogen ions to, as it states right there class, to regulate pH. So as that occurs class, this is what keeps you as well as me alive. So thinking about the buffer solutions and how it works, I'll give you a bit of an example class with buffers before I get to organic chemistry. So what happens class with buffers is we have class the carbonic acid bicarbonate buffer system. So what happens is we have CO2 plus H2O, carbon dioxide class plus water. And this reaction, in this case, I will have proceed from the left to right, from the left to the right, and it's done class by way of carbonic anhydrase. So what happens is it forms carbonic acid, H2CO3. Notice I said carbonic acid. However, class, it very well could be that it proceeds class in the opposite direction. So in the event class, we have a hydrogen ion plus bicarbonate, which is HCO3 negative, to proceed class from this right to left direction, of course. Then, of course, we could make more carbonic acid. Please keep this in mind because that carbonic acid bicarbonate buffer system is a very important class in resisting shifts in blood pH. So, of course, if you take what was carbonic acid class and it's broken down to, of course, donate hydrogen ions, of course, it would change pH. And if, in fact, class, you were to take that bicarbonate to, of course, accept those hydrogen ions class, the pH would shift in the opposite direction. Please keep this in mind because, as I just mentioned, class, the respiratory rate, be it hypoventilation or hyperventilation class, can definitely class alter pH dramatically by altering the amount of class carbonic acid in the blood. I hope you all wrote that down. Take it, class. I say, oh, the places you'll go. So now I'll get directly into class organic chemistry. So here with organic chemistry, just keep in mind, class, that it's all because of those copious amounts of what I call carbon and hydrogen. So with this, typically, class, depending on in what they are, they will dissolve in water or those organic liquids, organic molecules will. So those water-soluble organic molecules, they do not release ions, and they are not electrolytes. So think of those that we just finished, class, as being that part of inorganic chemistry. Well, we're now, class, getting into organic chemistry, with those things known as carbohydrates, class, lipids, proteins, and nucleic acids. So what's typical, class, is that inorganic molecules or compounds, they do not, class, contain the carbon and hydrogen. So they're typically class going to be those electrolytes that do dissolve in water. Oh, I heard that. So typical which with inorganic chemistry, we think of things such as those inorganic salts, carbon dioxide, oxygen class, and water. And they form ions. All right, so water class, you all know a lot about. I won't be here a very long time because we did a bit with water in our last chapter. But of course, it is that most abundant thing within class, living organisms. So with this, just keep in mind, class, that the solute class is what is inside, what is dissolved in a solvent, such as water. So the solvent class is a substance in which other substances are dissolved into. So next up, class is oxygen. Keep in mind, class, that we must have oxygen class. It is used by way of the mitochondrion class to synthesize energy based upon, of course, those metabolic activities. It's necessary class for life and survival. Up next, class is what is known as CO2. I mentioned class CO2 moments ago. Okay, all right, I hear you. I mentioned class CO2 not long ago. And I say that because it's a metabolic waste, meaning that is why class CO2 is around and it's here, because of the metabolism class of those living things here on Earth. It's of course also CO2 from other things, but majorly important class is a metabolic waste. And of course, it must class be removed from the body by way of exhalation. So from here, class, we get to those things known as inorganic salts. So with this class, I say some of the most important ions, I say class, influencing heart action are what they call potassium and calcium. Highly important. So potassium ions, see class table 2.6 on page 71. Take some time, class, and find out about it. So I'll go to calcium as well since I'm there. Calcium ions, class. If a person happens to be hypercalcemic, it would, class, affect the heart by increasing heart action and extending the contraction of the heart. If the person, class, happens to be hypocalcemic, it would depress heart action and cause, class, arrhythmias. With potassium ions, if someone happens to be, class, hyperkalemic, experiencing hyperkalemia, it will decrease the rate and force of contraction, as opposed to, class, having hypokalemia, which will cause him or her, class, to have arrhythmias. Sodium ions, class, if you want to know why they're important, it's an important, class, in muscle contraction. It's important, class, in nerve impulses. Sodium, class, is one of the most important things you'll learn about, as well as, class, potassium ions. So potassium, class, of course, allows us to get back to what we call resting membrane potential for repolarization purposes. We're not done. We're just getting started. So now, class, to what are known as carbohydrates. On your test, class, I say, you'll be asked, class, about these 4 classes of organic substances. They are, class, known as carbohydrates, lipids, proteins, and nucleic acids. You have figures such as figure 2.11, figure 2.12, figure 2.13, figure 2.14, figure 2.15, figure 2.16, figure class 2.18, figure class 2.20, and figure 2.21, and maybe even, class, figure 2.22. Let us begin. Carbohydrates, class, are used for cellular energy. Period. End of story. Meaning, that's why we eat. Meaning, we eat because we must have, class, carbohydrates. So I will not get into your personal lives ever. However, I'll put it this way. I would never go, class, on a no-carb or low-carb diet. We must have them. So let's now get to the way in which, class, carbohydrates are used. So carbohydrates, class, are used, and they're used, class, by the way in which they're classified. So carbohydrates can be classified, class, in one of 3 ways. They're classified as being A, monosaccharides, which are, class, those simple sugars. I say they're classified as being A, monosaccharides, class, which are those simple sugars. I'm confident, class, you have heard of these before, because I know you all eat. If you did not eat, class, you would not be alive. So let's begin. So monosaccharides, class, such as, I guess I'll begin with glucose, is a monosaccharide, including, class, deoxyribose and ribose, and even class fructose. Just a few examples, class, of monosaccharides. So again, I said monosaccharides, and their examples are glucose, fructose, ribose, deoxyribose. Oh, I left off one class. Add to that list galactose. Galactose. Next up, class, well, before I go to what's next, the monosaccharides class are what we use for energy. So by way of the mitochondrion class via respiration, called cellular respiration class, it is what synthesizes energy in the form of ATP. Up next class are the disaccharides. So that's when you have two sugars class covalently bonded together. So in that case class, we have examples being sucrose, maltose, and lactose. And if you're wondering, class, how do you get there? The way in which you get there, class, is sucrose is glucose and fructose bonded together. Maltose is glucose and glucose covalently bonded together. And then lactose, which you likely would find in milk, unless, of course, it's been removed, being glucose and galactose. Thirdly, class, the largest of those size classifications of carbohydrates would be the polysaccharides. So polysaccharides class are colossal molecules, and I would never draw those on the board because they're just that huge. So they are classed things such as starch, glycogen, and cellulose. As I've stated in such a way, class, we think of starch class as being there for storage. Storage class in plants. You find starch class many times, and of course a storage root class called the potato. Cellulose class is a major component of plant cell walls. They're structural. And most importantly, class, I say, is going to be what is known as glycogen. It's storage class in animals. So of course, we class store glycogen class in two places, our liver and skeletal muscles. I say again, we store glycogen class in two places, our liver and in skeletal muscle. So keep in mind, class, dietary fiber is good for us. So please eat more cellulose. I repeat, please eat more cellulose because of course it's indigestible. We cannot class digest it. Other animals can, not all, but we cannot. Moving it right along, Huff is to the lipids. So the lipids class, they are not water soluble, not at all, but they are soluble class in organic solvents. So the types of lipids class that are here and included are known as the fats or triglycerides, the phospholipids class, and steroids. So let's begin now, class, with the fats. So to help you all with these fats, I say please watch your fat intake. Not just you, but also me, myself. So typical of which class of fats is that they come in more than one type. Meaning fats class could very well be either those that are saturated fats, and those class known as unsaturated fats. So those saturated fatty acids class, these class come from animals, meaning things such as a steak. I'll just put it out there. Or things such as your beef you may enjoy, if you eat meat at all. So they have a single covalent bond, hence class they are solid at room temperature. I said mostly solid at room temperature. Please watch out for these, even though they may taste amazing. As opposed to class those unsaturated fats or unsaturated fatty acids. So the unsaturated fatty acids class, they have more than one class. So they have at least that double bond class. And that double bond that exists is why these class, which are of plant origin, meaning are from plants, are liquid at room temperature. These class, I say, are healthy for you and healthy for me. Thanks a lot, olive oil. So to help you out with it, class, one thing that I will mention is that please do not, I repeat, please do not ingest class coconut oil or even class palm oil, because these are typically class high in saturated fats, but are liquid class at room temperature. So the most healthy fats, of course, are that of olive oil, which I enjoy, and even class canola oil. So with this class, other things that can, I even wrote in my textbook class, be killer, are those that are known as hydrogenated oils. So what manufacturers class do is they add those hydrogen atoms class to certain vegetable oils to make them harder and easier to use. So these class are not good for us at all. And when I say class not at all, I do mean class not at all. For instance, if you happen to eat these things, class, they will likely occlude your arteries. And I did say occlude, or your artery. So one last thing to get to, class, are known as lipoproteins. So a lipoprotein, I'm helping you out, class, from your test, is composed of class A, a phospholipid class. And you can find this class, I think it's around page 699 if I'm not incorrect. Page 699 of your textbook. So a lipoprotein class is composed of a phospholipid, it's composed of cholesterol, it is composed of protein, and the triglyceride. Now I'm saying all of this because fats, class, structurally are made of that glycerol head you see here, and 1, 2, 3 fatty acid tails. That is what a fat is, or a triglyceride. So keep in mind, class, the low density lipoproteins, class, have a high cholesterol concentration. These are bad for you and bad for me. Please watch your intake, class, of these. On the converse, class, high density lipoproteins, which are good, have a high protein concentration, class, and a low concentration of lipids. And these, class, I say, are some of the best things on Earth for us, and it's because they're high protein content. To the second of three, class, the phospholipid. So the phospholipid, class, is very similar, class, in structure. It has one glycerol head and 2 fatty acid tails. To help you out with it, class, these are what make up our cell membrane. These are what make up, class, our plasma membrane of our cells. And I say that's the importance of it. So they are amphipathic molecules. And what that means is, class, they have a glycerol head, which is hydrophilic, and they have those hydrophobic, class, fatty acid tails. Thirdly, class, I'll get on down to, of course, the steroids. So the steroids are made of rings, as opposed to, class, the glycerols and fatty acid tails of the fats, class, and the phospholipids. So the steroids, they are, of course, widely distributed in the body, and they are needed, class, and I say in everything. So what do? Well, they're needed, class, to, of course, make up hormones, such as the sex hormones, estrogen, class, progesterone, and testosterone, but they're also needed, class, for cholesterol. We all must have cholesterol. It's a major component, class, of cell membranes, and to make the cells, I guess I'll say, not necessary, well, I'll say they're soft or pliable. Your cells, class, aren't hard, and it is, of course, because of cholesterol. We must have it. And the very same way, class, vitamin D, which is required for calcium to absorb, is by way of the thing called the steroid. Up next, class, I'll move on to the third of which, called the protein. So proteins, class, they're used in a number of ways. I'm here, class, on page 74. So they're either structural proteins, they're proteins, class, used as a source of energy, which doesn't happen often, or they can be used, class, as hormones. So as I do it this way, class, the protein is made up of the amino acid. That is the monomer, class, or that building block of the protein. So with this, class, let's get to amino acid structure here briefly. Amino acids, class, are made of a 3-piece. I did say a 3-piece, class. You say, what 3 pieces? Well, the amino acid, class, as it is in structure, it has, class, an amine group. The amine group, class, you see here is that NH2. It then, class, has what is known as the R group, and the R group, class, they're in an orange or a yellow, which gives, class, each amino acid its, I guess I'll say, unique properties. And then finally, class, it has its carboxyl group or its acid group, which of course is its namesake, why it's known as the amino acid. So as it happens, class, these amino acids that are coming together, class, covalently bonded, combined, of course, make up all of the proteins needed, and can even, class, synthesize, I would say, an innumerable amount, class, of antibodies, once, of course, you've come in contact with some antigen, unless, of course, the antigen kills you. I did say that. So please, class, wash your hands. So to help you out, class, proteins come in many forms, such as hemoglobin, class, and even myoglobin, which have that high affinity, class, for oxygen, and they carry the oxygen, class, in the blood and skeletal muscle, respectively. We also, class, have proteins known as actin and myosin. These are contractile proteins found in muscle, class. We'll learn about those in chapter 9. And then, of course, I mentioned those as being enzymes, those biological catalysts, class, that lower the activation energy in those metabolic reactions, class, ensuring that we don't have to have a fever, class, to break down, class, those things we ingest. by way of course, mastication, and then, of course, getting into the stomach, and then for absorption class by the small intestine. So having done that class, there are 4 levels of protein structure. So you have that primary structure, which would be that primary sequence class of amino acids you see here at A. Then class, you have that tertiary structure, that 3-dimensional class folding. You either class at B, have that alpha helix. Well, excuse me, I said the tertiary level. That's when you have the folding. So that 3D structure class happens, and then we get that secondary structure with the beta-pleated sheet class shown here, with the beta-pleated sheet class shown there, and the alpha helix class shown there. And then ultimately class, depending upon what protein it is, you have that quaternary structure. And that class is when you have 2 or more polypeptides, called proteins, of course, bonded together covalently. So lastly here, class, we've now made it on to what are known as the nucleic acids. So the nucleic acids, they, of course, like the rest of these class, are large, complex structures. So here, class, the monomer, or that small piece that makes up this large macromolecule, is known as the nucleotide. That's what you all see here, class. This is figure 2.20. So shown here, class, in that yellow or orange color, is that P. That's the phosphate group, class, the phosphate backbone that it is. In green, class, that S stands for that sugar, that pentose sugar, being either ribose or deoxyribose, class, respectively. And then thirdly, class, is that base, or that nitrogen base. So let's begin. That is, class, the nucleotide, made up of 3 parts: the phosphate group, that pentose sugar, class, and the nitrogen base. So there are 2 types of nucleic acids that exist, class. They are DNA and RNA. DNA, class, is deoxyribonucleic acid, and RNA is ribonucleic acid. I think my daughter's falling asleep. So it's the DNA class, which of course is double-stranded, that double helix, that is a responsible class for having, of course, for containing all of our hereditary information. So to make it make more sense, class, I guess I'll do it in such a way. So DNA class structurally contains the phosphate group. Its pentose sugar class is called deoxyribose, and the nitrogen bases class are adenine, guanine, cytosine, and thymine. Adenine class will always be paired with thymine. Guanine class will always be paired with cytosine. So A is equal to T, and G will always equal to C in the double helix. So what it does, class, is it stores our hereditary information. Everything, class, about you and everything about me is in my DNA, my A's, T's, G's, and C's. It also, class, is responsible for expression of genes, meaning it is what is encoding, class, each gene that, of course, will be expressed. And, of course, it codes for proteins. So you go from DNA to RNA to protein, which we just finished. Now let's get on over to what is called RNA. So RNA is known as ribonucleic acid. It is single-stranded, that single chain of nucleotides. So what happens with RNA, class, is that, well, let's get to structure first off. So with structure, class, it still has that phosphate group. Its pentose sugar class is ribose, and the nitrogen bases class, or nitrogenous bases, they are adenine, uracil, yes, it's a different class, uracil, yes, it's different, guanine class, and cytosine. So base pairing here, class, is A will be equal to U, meaning adenine will pair with uracil, and guanine will pair with cytosine. All the time. So what's different here, class, with this single-stranded molecule that's called ribonucleic acid is that this does not, class, last a long time. DNA, class, lasts a long time. If there's a crime, class, DNA is left somewhere, unless, of course, whoever that person was or is cleaned up, I guess, and thought they got it all. There is still something that left behind called DNA. DNA, class, is, I would say, in everything that's left. Ribonucleic acid doesn't last a long time. So you go from DNA to RNA to protein. And that, of course, is that central dogma of DNA. And that's how it works. So having done this much, class, I would say please study and prepare well for your exam. If I can help you, please contact me, class, via email or even by telephone by calling my office telephone number. This is your instructor, Scholar Huff, and this was Chapter 2.